Okay, so now let's go to this one. Let's move forward, and I would like to tell you about the young modulus of different things. So just a second. I don't think the streaming is showing anything. Okay. So some of the young modulus, you need to actually remember those, right? Because they might give you as a in the estimation question. So let's write young modulus. Let's write the names of materials. So basically, I will write all the young modulus in gigapascals, and you should remember that 1 giga is equivalent to 1 times 10 raised to the power 9 pascals, or simply let's write 10 raised to the power 9. Okay, now, so we're going to talk about aluminum, we're going to talk about concrete, we're going to talk about copper, we're going to talk about glass, and brass, and iron, and steel, and rubber, and we're going to talk about wood. Mostly you will see aluminum, concrete, copper, iron, steel, like that. But still, there's no harm to remember these two. So aluminum young modulus is 70 gigapascals, concrete is 40, copper is 130, glass is 70 to 80, brass is 90 to 110, iron is one of the toughest one, which is 200, steel is tougher, 210, rubber is 0.01, which is very small, and wood is just 10. Is it clear, everybody? Alright, so just remember this, right? This is very important in that particular sense, okay? So then let's just move to the next part where we're going to learn about some of the features.
Sir, what is the?
Yeah.
What is this?
These are the young modulus of basically the ratio of stress over strain of these materials. Okay.
Okay. Thank you.
No problem. Okay. So if you don't remember, I guess you guys have forgotten about it. Well, you shouldn't have, but still, let me just give you a little bit of feedback. So young modulus was basically stress over strain, and I taught you to how we actually find it out using this method. Remember, Aisha, now?
Yes, sir.
Okay. Now, so we're gonna learn some of the features of the graph, and let's see, it'll be fun. So the graph basically looks like this, mainly. And initially there is a straight line, and then the graph basically turns like this and like that. So this point is the limit of proportionality So you guys already know what that is. If you've forgotten, limit of proportionality is the point beyond which Hooke's law is not followed. Then next comes another point really close by, which is called the elastic limit. Elastic limit is the point beyond which, if the material basically goes, it doesn't return to the same shape again. And then let's use another color on the top of it. This is the maximum point, where we call it as ultimate. Tensile, or if it's compression, so compressive strength, which basically means that this is the point, because this graph is stress, pascals, and strain. So this graph, basically this point that I'm trying to show you, is the point which the material basically shows the maximum stress at. So this is stress and this is strain. Okay, and then finally you have this point, which is the cross, and that's called the breaking point. Breaking point means that beyond this point it just snaps. All right. Okay, so one of the points which are actually there as well, I wanted to do it. Usually they won't ask you, but we don't really know, so we'll do it. Just after elastic limit, there is a yield point, and now let's just segregate it. So till the elastic limit, if you check this out like this, and then this, let's separate them. The region you see right now, like this, is this too thick. This region is called the elastic region, because the material will come back to its original shape. But if it goes beyond this point, like elastic limit, this region that you see, this is called the plastic region. So plastic does not really mean that it turns to plastic. It basically means that it's something that shows permanent deformation that cannot be, reversed. So that's why it's sort of that. Okay, now, so let's define some of them. That's important, because some of them we have already done, or we could define all. I don't know. Okay, let's define all, just to remind you. So first, limit of proportionality. It will be asked very often. Then we're going to look at elastic limit. Then we're going to look at the yield point. And then we're going to look at ultimate, tensile, or compressive, whatever it is, right? Strength. So tensile means that it is in tension, compressive means it is in compression. But that's basically, we're talking about the same point. And then we're going to talk about the breaking point. So first of all, let's see, for this one, this is basically a point till which force is directly proportional to the extension. Elastic limit, a point beyond which a material does not return to the original shape after unloading. Unloading means that when the force is removed. Okay. Then comes yield point, a point beyond which material shows large change in stress with less change in strain, which means it's in I wrote large change in strain, basically I have to write. Sorry, my friends. Large shows large change in strain with less change in stress. So basically, it's sort of basically it's elongating more, changing the shape more, but taking very less force on it. So that's something. Ultimate tensile strength is a point beyond which a point at which, let me change this eraser, it's so annoying. A point at which the material takes the greatest stress without breaking. That's important. And finally, the breaking point, a point where the material fractures. Basically, it snaps from the weakest point. Alright, everybody understands this? Please let me know if you do not. Okay. Hamad, Javeria, you guys understand this? You guys can hear me, right?
Yes, sir.
Okay.
Yeah, we can.
Okay. Okay, write this down then. Damn. Okay, should we start? Should we start the next thing then?
Yes, sir.
Okay. So now let's do some of the examples. So suppose they've given you something like this, a wall on the top, and then they have given you this and sort of this, right? Said, okay, this is copper and this is steel, and there is a weight hanging. Okay. And now they've said, question they say, Young's modulus is twice of copper Young modulus is twice of steel than copper, sorry, and then say a 50 centimeter length copper wire of diameter 2.0 millimeter is joined to a 50 centimeter length of steel wire of diameter 1.0 millimeter, making a combined length of 1.0 meters. Okay, so this is what they've written. Now they say wire is stretched by a weight. So they say calculate ratio extension of steel wire over the extension of copper wire. Do you guys understand the question? Okay. Now, whenever you have these sort of questions, I just want to tell you that it is best to make a table, okay? Because there's so many values you would basically forget. So if you remember, Young's modulus was given by FL over AX, where F was the force, length was L, A was area, X was the extension. Basically, this is a form of stress over strain that we derived up. Okay? Now, what you're going to do is just write this down. Right now, we have basically, they're talking about diameter. So we're going to write Young's modulus first, then we're going to write F, then we're going to write L and A and X and the diameter separately because we do have that. Okay, so once you made this, so we're going to write copper here, we're going to write steel here, and then we're going to just fill in the values. Okay, now the thing is that it says Young modulus of steel is twice of copper. So if I say Young modulus of copper was E, the Young modulus of steel was twice of that E. Do you guys understand this?
Yeah.
So just like we're going to fill that. Because they are in series, so whatever the weight, oh my god, whatever the weight is acting, that would be the same on steel, same on copper. With series, the force remains the same, so we're going to write W here, to date W. Both have the same length, which is 50 centimeter, 50 centimeter. And now area is not given. The extension on copper is what we need to find, and extension steel is also needed because of the ratio. But the diameter is given. So if you look at it, the diameter of copper wire is 2 and the diameter of steel wire is 1. So this is 2 millimeter and this is 1.0 millimeter. Okay. Now because we know that area of any circular object or even something like that, so area is pi by 4d square, which means that the diameter of basically diameter of, if we say the steel is A, then naturally a square, like if you square 2 times, so this is going to be 4A. Do you understand this? Do you understand what I did? Because this was, if this is the diameter D and this is 2D because of its double, so area will be 4 times the A. You get my point here?
But why is it 4?
Because there is a square in the formula, right? So D square is proportional to A, right?
Yes.
So if it's 2, area, if the diameter doubles, area is going to be increased by 4 times. That's why. Okay.
Yes.
Should I go forward then?
Yep.
Now what I'm going to do is, what do I need? I need, what is this? How's the color changed? Anyway, it's gone now. So the formula is E equals to FL over AX, and I need X. So can I say X is equal to FL over AE? So I'm going to make the subject that's needed here. For steel, wait a second please. These questions will take some effort, so you guys need to practice it a lot. So what I'm going to do is, I need this ratio where what I'm doing is, I need extension of steel over extension of copper. So extension of steel can be written as, force on steel was W, the length on steel was 50, area of steel was A. So I'm just writing the steel things here, and the Young's modulus of steel was 2E, and what is divided? The extension of copper. Now let's look at copper. So force was W, the length was the same, area was 4A, and the Young modulus was just E. Do you guys understand what I've done? Now I have intentionally put this sign because when I remove this, basically this is going to take a reciprocal here. And when it does, now we can cancel out stuff like 50 goes with 50, W goes with W, A goes with A, E goes with E. Now what you get is 4 on the top is left and 2 is left at the bottom. So the ratio is 2:1. Do you guys understand? And that's what we're looking at. This is around.
Sir, how did you know to put steel on top and copper on the bottom for the ratio?
They asked in the question, see?
Oh yeah, okay.
Okay, do you understand now? So basically, if you
Yeah.
follow what I'm doing, it will really help you quickly do this. Otherwise, the equations will be too long, too complex, and you will be pretty confused that what is really happening. So always write them like this, and like 99% of time they're going to give you a ratio question, especially in paper 1 like this. Understood?
Yes, sir.
Okay. Now let's do another type of question then. So in 10 minutes you guys need to rejoin the same link. Let's do an example. A metal wire of cross-sectional area 0.20 millimeter square hangs vertically from a fixed point. A load of 8 newtons, 84 newtons in fact, is then attached to end of wire. The increase in length is 0.30%. Okay. Now it says what is the Young's modulus? Now in these sort of questions, when there is no comparison, you just need to write the things. Like for example, the force here is 84 newtons. The area is given in 0.20 millimeter square. So 0.20 millimeter square needs to be converted. How to convert millimeter into meters? So 1 millimeter can be written as 10 raised to power minus 3 meter. We know this, right? So if you square this up, so 1 millimeter square is going to be 10 raised to power minus 6 meter square. So what I'm going to do is I'm going to write, instead of millimeter square, I'm going to write 10 raised to minus 6 meter square. Do you guys understand this? Now, the next thing is given is percentage strain, which is the increase in length, which is given as 0.30%. And of course, you can change it. You can write 0.30 divided by 100, which is just 0.30 times 10 raised to 1 minus 2 in that case. Okay? Now, Young's modulus is given by stress over strain. Stress is force over area, which is 84 divided by 0.20 times 10 raised to minus 6. And this whole stress is divided by strain, because strain is already calculated, like they've given it, so we don't need to do anything. When you put that in your calculator, so be very careful, because if I were you, I would put it like this. I'd first make this symbol and then this again, and then I'm going to write 84, and then I'm going to write 0.20 times 10 raised to power minus 6, and then I'm going to write 0.30 times 10 raised to power minus 2, and that gives me 1.4 times 10 raised to power 11 pascals. Understood? So do remember that. Okay, so this is a pretty simple question. Please write this down, and then we'll move to the last question for today. Okay, everyone, you guys have written it. Should I go forward then? Okay. All right, now the next thing you guys need to do is let's do the next question now. This I really need to, just okay. So let's do the example. Now they have shown a figure like this. And this is T, like this. And they say a steel bar of cross-sectional area is under tension T. Diameter of wide portion is double the diameter of narrow. Now it says what is the ratio of stress in wide portion over stress in narrow portion. That's what they've asked, okay? Now, because this is not about the Young modulus, it is just about the stress, okay? So what you're going to do is, you're going to put in the things we need. For stress, basically need force, area, and because there's a diameter, so I'm going to include the diameter as well. So we're going to write wide here, we're going to write narrow here, you can do alternate as well, and then fill in the values. Because both of them have the same force, so T and T, the diameter of wide is basically twice the diameter of narrow. Do you guys understand this? Because area is proportional to diameter square, which means this is going to be 4 times the area, this is going to be just area. And now just use the ratio. So what do we need? We need stress in wide over stress in narrow. So stress in wide is going to be force over area divided by force over area. And now I'm just gonna take reciprocal. You cancel this stuff out and you'll be left with 1 upon 4, which is just 0.25. Understood, everybody? If you have any questions, please let me know. When the meeting ends, please rejoin. All right. So why wouldn't you work, my friend? Okay. So you guys have written this. Should I go forward? Now, so we're going to do a small derivation, and within that small derivation we have this hidden thing, and then we'll basically end the class. So we're going to look at the relationship between spring constant K and Young's modulus. Okay. So force is equal to Kx, and we learned Young modulus is F times L over A times X. And now if I write K, make the subject, so it will be written as F upon X, and then the Young modulus is going to be, if I write it as F, if I just write it like this, you guys won't mind, right? It is the same thing, no? Okay. So this F upon X, if you look at it, it's just the same thing as here. So we're gonna put it right here. So Young modulus then will be K times L upon A, because length and area is just constant value, so it means E is proportional to K, which basically means that Young's modulus also represents stiffness of a material as it is proportional to K. All right. All right then. So that would be it from my side today.